So far, we have just discussed mostly about the mechanic of neural networks. Today, we're going to talk about a particular kind of neural network called convolutional neural networks. So here we go. Computer having trouble recognizing seemingly trivial perception tasks, such as detecting a puppy in the picture or recognizing spoken words. And that happened for a long time. Now, for human, we are really good at this, but most of the time we cannot explain how we do it. For example, we can look at the picture of this puppy in the low corners here. Not only do we know that's a puppy, but we also notice how cute it is. Right? Or you can replace that picture of the cat in the same way. So, since the advent of convolutional neural network, computer is now able to tackle this challenge. A bit of the inspiration from the architecture of human visual cortex. In 1981, David Hubel and Toyson Weisel showed that neurons in our visual cortex have a small local perceptive field. What does that mean is that our brain actually recognizes small patches in the image that our eye perceives. So for that discovery, they received a Nobel Prize in 1981. And the way the human brain works is that some neuron would have a larger receptive field and they react to more complex pattern based on the output of those lower level neuron with small local receptive field. This make a human brain a powerful architecture that enable human to recognize all sort of complex pattern. Now, the convolutional neural networks, or short for CNNs, are inspired by this visual cortex architectures, and it was proposed in 1998 by Yann LeCun and his paper called the LeNet 5 architectures, which used to mostly recognize handwritten numbers. The name convolutional indicate that the network employ a mathematical operation called convolution. We will talk about convolution in the next slides. And the convolutional neural net CNNs have convolutional layers and pooling layers. So you want to flash the architecture of the LeNet 5 here, and along with the image of Yann LeCun. You might recognize him as one of the winner of the Turing Awards. So, convolutional layer. The convolution operation is taken to two input. It's the multi-dimensional arrays of real values. The first input is the array of real data, the input data, and the second is the called a kernel, which is a multiple dimensional array of parameters, in this case neural network parameters. And for images, we're going to use 2D dimensional input image I and 2-dimensional kernel K. So first, we put the kernel on top of the image and then compute the dot product of corresponding pixel. And then we move the kernel slightly to the left. So we move it in the left, right, and then up, down at 1 pixel at the time, and then repeat step 1. And as the result, our output image is also a 2D image. So let me explain this in a pictures here. Right? We have the input image, and we lay the kernel on top of the input image here, right? So the kernel have W, X, Y, Z, and the input here is A, B, and E, F. So what happened, it would take the corresponding pixel. So W would be correspond to A, B would be correspond to X, and so on. So at the dot product, we have A times W plus B times X plus so on and so forth. And that will be the result of a pixel on the output image. Again, if we move this kernel 1 pixel to the left, now it's laid on top of this image like this, and we calculate the dot products again. And at the result, B correspond to W, C correspond to X. So in the output image, we now have B times W plus C times X plus so on and so forth. So we keep doing this, move the kernel left to right, up and down to the image, and at the result, we obtain an output 2D image of this kind of dimension. So that's all about convolutional operation. So why use convolution? It turns out that convolution have very important property that improve machine learning system. Number one is sparse interaction. Number two is parameter sharing. And number three is equivalent representation. So let's talk about each and every one of them. Property one, sparse interactions. So as you already know, traditional neural net have a dense interaction. What it means is every output interact with all of the input from the previous layers. This creates a very dense connection as you see here. Now, convolutional neural network have a sparse interaction. What it means is that one of the output only interact to a subset of the input neuron. In this case, we call this a receptive field. Now, the receptive field, which also means this is a kernel input, and the kernel input have 10 of pixels instead of thousands of pixels like the dense network. So at the result, we have fewer parameter, fewer memory requirement, and also improved statistical efficiency. That we reduce from big O of n by n to big O of k by n, where k is several magnitudes smaller than n. So we utilize the receptive field idea to apply to convolutional neural networks here. So this is all inspired by the neuron, and it's very similar to the biological neuron. The neuron in the first convolutional layers only interact with a subset of the pixel in the input image, like the rectangle down here called the receptive field. And then the neuron from the second layer only interact to a subset of neuron on the first convolutional layer. So you can think about this at a first convolutional layer, maybe focus on a low-level features that compute from the input image, and then the upper convolutional layers are compute higher-level feature based on the computed neuron from the lower hidden layer. And this worked very well for object recognition, as you will see. Now, the second property for convolutional neural net is that parameter sharing. And it's a really nice property. Traditional network utilize the weight matrix exactly one when compute the output. So by this single black arrows here. Now, for convolutional neural net, this weight is used more than one. In fact, if you look at here, for every output, it utilize a weight from every single input location. And this is basically all of these arrows mean just the parameter u in the kernel, right? And we know the kernel is applied at every single input location. And so instead of learning a separate set of parameters at every location, we learn only a single set, which means we save on storage. Now we have a matrix k by k parameters and set up m by n. And we already know k is several magnitude less than m and n. So let me explain this efficiency in the application of edge detection. So the right image shows the strength of all vertical oriented edge of the input image of a dog. So you can think about this as a highlight of vertical edge. And the way it's calculated is that it takes every pixel in this input image and then subtract the value of a neighbor pixel to the left. So all it does is just subtract the neighboring pixels here to compute the different, right? So for example, you can see this is really strong edge. Why is it strong edge? Because when you take a black pixel here and you subtract a white pixel, you see the hue different, right? So all the edge in the image become emphasized. And we can accomplish this using convolution. So taking two images from the input image, maybe A and B is here, and we're gonna convolve it with a kernel. And this kernel, we design it to be -1 and 1. And the reason for that is, as you see here, when you convert it, it basically means that A times -1 plus B times 1, which is equivalent of B minus A, which is exactly what we want to do. Now, with this convolution, there is actually only 3 operations, right? You do multiplication, 2 multiplication, and 1 addition. So there are 3 operations for every pair of pixels. At the result, the convolutional kernel contains 2 elements result in 319 times 280 times 3 operation to a total of 267,960 floating point operation. Now that compared to matrix multiplication, which I denoted down here, would require up to 8 billion operations. So we save a lot on computation using convolutions instead of using purely matrix multiplication. Now, you notice there is a drop in 1 pixels here. Instead of 320, it becomes 319. And that is what happened when you move this sort of kernel across the image toward the edge of the image, and you have like 1 pixel left. So you reduce the image by 1 pixel by this 2 by 1 kernel. So that's why we lose a pixel as we move across the image, right? So there is only 319 position you can put this little kernel across the row of the image. All right, cool. Property number 3 is the equivariant representation. And what does it mean is that it is invariant to translation property. So a definition of the equivariant is that if the input changes, the output changes in the same way. For example, if you have, let's have function g's apply on this image at position x and y, and what we do is here, it just shift the horizontal of the input 1 pixel to the left. That's all we do. So what happened is when you apply the convolution on this resulted g on image I, it's going to be equivalent of applying g on the convoluted version of I. So this could be equivalent, right? So what does that mean? It means that the convolution actually create a map where a certain pattern appear in the input. And it's going to be great for detecting a certain local feature that appear in the input. So this help us create a what called a feature map. Right? So let me explain. Say if you have an image of an X here, and you want to detect maybe a feature, meaning that you have a diagonal bar across the image like this. So you want to detect sort of a cross from left to right, top to down, like this, right? So applying convolutional operation on this input image, what you receive is a map. And this map, what it means is when you apply this on top of this image, you get some response back. And you notice here, this response or this map also tell me where is this features or this pattern appear in the input image. You see here, when you see really high response, like 1 here, it means that in that position in the image, this pattern appear. Like you can see here, if I apply it right here, you can see if I do a dot product here, my input will be very, very strong. And then it may be strong along this diagonal line, right? And not very strong in this diagonal line. You see here, this is not very strong here, but very strong here. And so on and so forth. You can see it kind of low everywhere except for this diagonal line. So what it means is I was able to detect this diagonal cross of an X in my image. It's a nice map for my feature or my parent here. Okay, so what I can do is I can detect many of these different features on the input image by stacking them together. So we can simultaneously apply multiple kernel, which is little patches here, on the input and then get a stack of feature map. Each of these feature map detect a certain patterns in my image. For example, I have another one detecting the across from right to left here. So it can detect this pattern. So in the feature map, you kind of see the high response here, right? Or I can try to detect like an X here with, you see the middle pixel here kind of covered, but it's really high, the white pixel, which you detect this pattern right here in the X image. So I now have a really nice way to detect multiple patterns, local pattern in my input image. And for representation, because we have multiple 2D feature maps stacked together, we typically represent it at a 3D map. So you can think of this stacked together into a 3D array. Right? And another really nice property for this is that it also follow a spatial hierarchy, which means the first layer compute some local pattern like the edges. You see an image of a cat. You compute some local edges like the edges around the ear and things like that, all edges. And then you have the second layer to combine these edges together to detect maybe an eyes, a nose, or an ear. And then you have even a higher level to detect actually the identity of that object, which is cat in this case. And you also can see this in more specific 2D image here. First, we start with detecting low-level feature that look like this, and then we use low-level feature to compute mid-level to high-level, and eventually we'll be able to separate it using some linear classifiers. So that essentially a really nice property for convolutional neural networks to follow. Now we do have some hyperparameters to tune. Number one is the same or zero padding. So what happened, I mentioned before about the input image gets string a little bit when you apply a kernel on top of it. And depending on the size of the kernel, you may string the image by a lot. And this figure right here actually show you, right? So if you have these neuron compute a single output, what happened is you can't really compute these neuron out here because you don't have a padding. So your output string a little bit, and if you do that multiple times, your output keeps stringing, right? So how do you prevent this output from stringing? You pad both sides of an array so that you can compute all of these images as well. So the input you see here remain the same throughout the operation, which is a very nice property, right? So you pad, typically we pad these with 0 neuron, and it remains the same size, so that we call it the same padding. And here I'll show you another example how it's applied on the image. So I pad the image around the image with 0, and so when I apply my convolution, my output image now had the same size as the original input image before I pad it. So my size remain the same here, as you see. Okay. Another hyperparameter we can use is called the stride. And what happened is that the stride would make the image shrink faster. And there's a reason why you want to image shrink faster for computational issues and things like that. But you can skip a pixel when you move the kernel across the image. Instead of moving 1 pixel at a time, you maybe move 2 pixels at a time. That's stride of 2. And that would downsampling the input image to maybe half the size if you move stride of 2, and so on and so forth. This is kind of similar to pooling layer, which we will see next. Pooling layer. So pooling layers, the goal is to subsampling the input image in order to reduce the computational load, memory usage, and also the number of parameters. So for example, if I look at this 4 pixel local neighborhood here, I can simply pick the maximum pixel and then use that as my output. And so on and so forth. I'll do that again for all the image here. And at the result, my output image is only a quarter the size the input image. I show you here in actual image size, right? So you can reduce it. And, you know, you can think about this 4 pixel neighborhood is like the perceptive field, and I pick the maximum response pixel out of this field, and I have a smaller image. So pooling neuron had no weight. You don't have to train it. It just simply aggregate the input into using a max or an average function. At the result here, the output only a quarter the size of the input, right? So 75% of the input value was dropped. Only the strongest response remained. So give me more specific, this is a 2D matrix here, and what happened is I can apply the max pooling, and I receive a output matrix only half the size. So what happened is I consider the receptive field, I feed it into a max function, I pick the maximum. In this case, for this 4 value, 1 is the maximum, so I put there, right? And you can repeat the same for the next receptive field. In this case, or 0.33 is the max, so I put it there, and so on and so forth. Right? Okay, So what happened is MAC pooling also have a nice invariance property. So what happened is this top figures show the output of MAC pooling. Consider only 3 in the input, right? So this one right here, consider 1, 2, and 3 at input pixel and pick the maximum, right? So what happened is that if I shift this input to the right by 1 pixel, which is down here, I shift everything to the right by 1 pixel. So 0.2 here become 0.2 here, 0.1 here become 1 here, 0.1 here become 0.1 here, right? So now the input had changed dramatically. But if you look at the pooling layer output, only half of this changed, right? In fact, these two values in the middle stay the same, which is very nice property, because you can think about it is kind of give invariant to small translation in the input, right? So it's a nice property to have. So next we're gonna see how the layer gets stacked together. So we have an input image, we can feed it through multiple convolutional layer, maybe feed into a ReLU to do some nonlinear mapping, and then pooling to reduce the size. At the result, you may have a stack of smaller feature map. And you can keep doing this together with more block after the others. And at the end, you may feed it into a fully connected network and feed a softmax operation on it to receive the probability of a certain label, right? So that essentially how the whole pipeline turns out, right? And if you want to look into more detail, I actually provided a toy example in the bonus slides, so you can try it out for yourself. Now, how do you implement this CNN architecture in Keras, right? And Keras provides a very easy way to make the CNN to sequential model. So you start with a sequential model, and you're gonna start feeding some convolutional layer in 2Ds here to con 2D. You're gonna use the first parameter is number of feature map you like to have. So in this case, I want to have 64 different feature map. Each of them have a kernel size of 7. So the kernel always going to be a square matrix. So when you put 7 here, it is going to be a 7 by a 7 square matrix. And then you can specify what the activation, what kind of padding. Here I use the same, so I don't want to string my input size. And then I feed in the input shape. In this case, a 28 by 28 dimension, and it's the grayscale image, so the third dimension will be just 1. And then after that, I feed a max pooling layers with 2. So this is a 2 by 2 consideration. What happened here is, like you see in the example, it's gonna string the input by 75%, or string by half and half with half height. And then I can feed another 2D convolutional layers. This case, I increase the number of featured map I want to use to 128, but my feature map going to be smaller, 3 by 3 matrix, some activation and padding, and so on and so forth. You can sequentially feed in multiple layer of convolution, and then pooling, convolution, and then pooling. And toward the end, you're going to flatten out the output. And what does that mean is most of these input is going to be a 2D image, but toward the end, you want to have it flatten out at a 1D array so that you can use dense layer. Dense layer is nothing but a regular neural net layers. And you know, you have 128 node, 128 neuron here. You apply some dropout, sure. We apply some dropout regularization, more dense, more dropout, and dense again. But this dense layer is special because we use softmax at activation. So at the result of this architecture, you can train the network to learn the parameter of the kernel, right? Remember, the kernel contains nothing but network parameters. So you may initialize this as some random value, and you're gonna use back propagation, gradient descent, to learn this weight, right? So you may start with random, so you have a lot of error, and you're gonna use backdrop to remove this loss errors, and then you use the gradient to update each of the weights. So the 0.5 maybe update to 0.6, 1.2 update to 0.9, so on and so forth, and then you update it through many iterations to reduce the errors. And eventually you may arrive with some conversion, which is the final settings of the kernel matrix. In this case, 1, -1, -1, and 1, with minimums the errors on the training set. So nothing changed. You gradient descent backprop just like any other neural net, but we're gonna tune it based on the parameter of the kernel. And keep in mind though, because this kernel is in 3Ds, multiple kernel stacked together, you're gonna learn a 3D weight matrix instead of a 2D that I showed here. Now we can test our CNN on a fashion MNIST using Spark categorical cross entropy at our loss function and atoms at our optimizer, right? Things that are relevant in the past, you want to put it here. Matrix accuracy, we're going to calculate the matrix using accuracy. And then you feed in training data, train on 10 epoch, and test and validate it on a validation test. Here we go. And then eventually we evaluate. So it shows the validation loss, what is the accuracy on the train set, what is the loss value right now. And so you see the loss value get reduced over time, while the validation accuracy increase over time. Very nice. It means you done the training correctly. And then eventually you test it on the test set, and you get an accuracy of 90%. Not state of the art, but pretty good to classify 10 class in this fashion MNIST dataset. Okay. Here, lastly, I want to show you an example of CNN classifier image taken from a Fei-Fei Li group at Stanford, and they was able to detect images of a cars here to a fully connected layer. This is high probability. It's also detect other probabilities, but you can see the layers of convolution, ReLU, Pooley layer, and so on and so forth. So this is it for the convolutional neural net. Next video, I'm going to show you how these architecture work on classify a massive data set called the ImageNet and how they've been winning the competition in the past years. So see you in the next video.